This video will cover the information in your Chapter 4 packet, sections 4.1 through 4.4. Section 4.1 deals with the general properties of aqueous solutions. So the first question says, do you agree or disagree with the following statement? If a solid dissolves completely in water, it is classified as an electrolyte. So on page 117 in your textbook, there is a picture of sucrose dissolved in water and sodium chloride dissolved in water. One of them is a non-electrolyte, the other is an electrolyte. So if sucrose dissolves completely in water and yet does not conduct electricity, then you would disagree with this statement, because clearly the ability of a solid to dissolve in water doesn't indicate whether or not the substance behaves as an electrolyte. And sucrose is an example. Modify the statement so that it is more accurate with respect to the definition of an electrolyte. On page 117 it mentions that an electrolyte is a substance whose aqueous solutions contain ions. So you might say the following: if a solid dissolves completely into water and there are ions present in the solution, then it would be classified as an electrolyte. In this question, we are supposed to write equations for what happens when these substances are dissolved in water, so we're going to try to decide if they are electrolytes or not. First example is magnesium chloride. It is an ionic solid, so it is an electrolyte. It breaks up into magnesium ions and chloride ions. Next example is methanol. Methanol is a covalent or molecular compound. It does not break up into ions, so it dissolves in water, but it stays intact as one molecule, one formula. Potassium hydroxide is ionic and breaks up into ions, and so notice the difference between methanol and potassium hydroxide. Even though they both contain OH, methanol is considered an alcohol, and that is not going to release hydroxide ions, whereas potassium hydroxide does contain ions. Next example is ammonium sulfate, and even though there are no metals in this formula, it is considered an ionic compound, so it breaks up into ammonium ions and sulfate ions. We have we have glucose. Glucose is covalent, molecular, not going to break up into ions, okay, like most sugars would do that. Hydrochloric acid, it says aqueous, but it is an acid, so I'm just emphasizing the fact that acids, when dissolved in water, will typically dissociate into ions, and we know that hydrochloric acid is an example of a strong acid, so it completely breaks up into ions. We have aluminum nitrate breaking up into its ions. And then finally we have another alcohol. This is ethanol, so it stays together as one formula. It is a non-electrolyte. Alright, in this particular question it says, which of these diagrams best represents a solution of potassium chloride? We know it cannot be choice D because potassium chloride should break up into ions, but I haven't really talked about the orientation of the water molecules around the ions. Let's see if there's any information in your textbook. On pages 117 and 118, it talks about water being a solvent for ionic compounds and says that cations are attracted by the negative end of water, which would be the oxygen portion, and anions are attracted by the positive end, which would be the hydrogen portion. And you can see in that diagram that the hydrogens are pointing toward the chlorine ion, and the oxygen is pointing toward the sodium ion. So based on that orientation, the correct answer for this particular question is A, since the oxygen points toward the positive cation and the hydrogen points toward the negative anion. Section 4.2 is referring to precipitation reactions. And you know from your textbook, this is on page 119, that a precipitate is an insoluble solid formed by a reaction in solution. These are examples of ionic compounds, and based on the table on page 121, we should be able to determine if they are soluble or not. Our first example is zinc nitrate, and all nitrates are soluble. We have cadmium sulfide, but most sulfide compounds are insoluble. We have lead, Roman numeral 2, acetate, and acetate compounds are soluble. Ammonium carbonate, and most compounds, all compounds that contain ammonium ions, are soluble. We have silver chloride, and there are chlorides that are insoluble, and they include silver, mercury, and lead. So silver chloride is insoluble. Most phosphates are insoluble, so calcium phosphate does not dissolve in water. Again, exceptions to the bromide rule include silver, mercury, and lead, so lead bromide is insoluble. Most hydroxides are insoluble, however, the exceptions include alkali metals, calcium, strontium, and barium. So barium is classified as a soluble compound. Group 1, or alkali metal cations, are soluble, so sodium sulfate is soluble. And then finally, hydroxides that are soluble include alkali metals, calcium, strontium, barium. Nickel is not an exception to that rule, so in general, nickel hydroxide should be insoluble. So the solubility rules will be given to you for application on quizzes and tests. And it's a good idea to be familiar with them, but you don't have to memorize them. All right, now we're going to write 3 different types of equations for a precipitation reaction. First, we write the molecular equation. Then we're going to write the complete ionic equation. And after removing the spectator ions, we'll write the net ionic equation. So here's the molecular equation for sodium carbonate reacting with magnesium sulfate. Our products from this reaction are sodium sulfate and magnesium carbonate. Notice that I've put an S next to magnesium carbonate because according to the solubility rules, it is insoluble. So magnesium carbonate is the precipitate that forms in this reaction. The complete ionic equation is based on whether or not we can break up this particular formula into ions. Sodium carbonate is broken up into ions, magnesium sulfate is broken up into ions, but magnesium carbonate is left as one formula since it's a solid precipitate. We break up sodium sulfate into ions, and this now helps us identify the spectator ions. If we look on both sides of the equation, we can see that sodium and sulfate are soluble, aqueous, on both the left and the right sides of the equation, so these are the spectator ions. Once we eliminate those, we now have the net ionic equation for what happens in the formation of magnesium carbonate. So that net ionic equation only lists the ions that come together to form the solid precipitate. Will a precipitate form when barium nitrate and potassium hydroxide are mixed? So the product we get would be barium hydroxide and potassium nitrate. Notice that both of these substances are soluble. Well, if both substances are soluble in water, then there would not be a precipitate formed in this reaction. Now we have to consider whether or not a precipitate would form from the combination of these various aqueous solutions. So zinc nitrate and magnesium sulfate would produce zinc sulfate, which is soluble, and magnesium nitrate, also soluble. So no reaction would occur, as in no precipitate is formed. Our next example, we would get silver carbonate and potassium nitrate. The precipitate would be silver carbonate. Then we get calcium chloride and copper hydroxide. The precipitate would be copper hydroxide. Lithium bromide and barium sulfate are the products in the next reaction, and the precipitate is barium sulfate. Then we have sodium phosphate and potassium acetate. Those both contain group 1 cations, so no precipitates would be formed because both products are soluble. Lead bromide and sodium nitrate are produced. The precipitate is lead bromide. And then sodium chloride and nickel phosphate are produced. The precipitate is nickel phosphate. Now that we know the 5 reactions that produced precipitates, we have to write the net-ionic equation. So with these 5 substances listed on the right side of the arrow, what goes on the left side of the arrow are the ions that come together to form that precipitate. And notice that in some cases I have to balance the equation by putting coefficients in front of the particular ions. So now we're on to section 4.3, which has to do with acids, bases, and neutralization reactions. Acids are substances that ionize in aqueous solution to form protons or H+ ions, and acids are often called proton donors. There are many examples of monoprotic acids. I'm just going to list 2. So hydrochloric acid, HCl, nitric acid, HNO3. Monoprotic because they contain 1 hydrogen atom. And sulfuric acid, H2SO4, is a diprotic acid because it contains 2 hydrogen atoms. When a single arrow is used in an ionization reaction, we say that the substance that ionizes is a strong electrolyte. On the other hand, if double arrows in opposite directions are used, we say that the substance that ionizes is a weak electrolyte. These equations for the first and second ionizations of sulfuric acid are going to show you that the first proton that comes off, the first hydrogen ion that comes off of the formula H2SO4, is completely dissociated, so that's why a single arrow is used, but HSO4- does not ionize completely. So the second proton comes off, but not 100% of HSO4- is ionized. That's why we use double arrows. For part F, when it says circle the hydrogen that is ionized, let me call your attention on page 124 to the structure of acetic acid, CH3COOH. They mention that acetic acid has 4 hydrogens, but only one of them, the hydrogen in the COOH group, is ionized. The other 3 hydrogens are bound to carbon and do not break their CH bonds in water. So we're going to circle the hydrogen that's attached to the oxygen in the COOH group, and then in benzoic acid we can see a similar group, and we circle that hydrogen. Bases are substances that accept H+ ions, and when they dissolve in water, they produce hydroxide ions. Ammonia is an example of a base. So as a proton acceptor, it pulls the hydrogen from water to produce ammonium and hydroxide. And you can see in figure 4.7 on page 125, they're showing you the transfer of a hydrogen from the water to the ammonia, and ammonia turns into ammonium, and the water turns into hydroxide when that hydrogen ion is transferred. Acids can be defined as either strong or weak. It says circle the 7 strong acids. So all of the other acids are weak acids. We circle sulfuric acid, chloric acid, hydrobromic acid, hydrochloric, perchloric acid, nitric acid, and hydroiodic acid. Any acid from this list that was not circled is a weak acid. So on page 125, at the bottom, table 4.2, it lists the 7 strong acids. And it also talks about strong bases being soluble metal hydroxides. So again, these are the names and formulas of the 7 strong acids. And it's a good idea to memorize these. That will help you write net-ionic equations for acid-base neutralization reactions. So the strong bases include soluble metal hydroxides, such as alkali metal hydroxides, and some of the alkaline earth metal hydroxides like calcium, strontium, and barium. Other examples of weak bases besides ammonia include compounds known as amines. An amine is a derivative of ammonia in which one or more hydrogen atoms have been replaced by carbon atoms. The lone pair on the nitrogen is what is going to bond with a hydrogen atom from water. So in this case, we have a compound known as methylamine. The nitrogen is going to form a bond with one of the hydrogen atoms from water. And when the HO bond breaks in water, it forms the hydroxide ion. So we produce methylammonium as a positive cation and hydroxide as a negative anion. Dimethylamine is going to react in a similar way. Again, the nitrogen is going to acquire a H plus ion. So dimethylamine now becomes the dimethylammonium ion, and we still form hydroxide in the same way. Trimethylamine is going to react with water, picking up the H plus ion from water, forming the trimethylammonium ion and hydroxide again. Part M is asking us to classify different compounds in terms of their electrolyte abilities. If a substance is soluble in water and it is ionic, it is a strong electrolyte. If a substance is soluble in water, is covalent, and is a strong acid, it is a strong electrolyte. However, if this covalent compound is a weak acid or a weak base, it is a weak electrolyte. And if this covalent substance does not conduct electricity at all, it's because it's neither an acid or a base, so it is a non-electrolyte. So we have 12 compounds, and they have to be classified either as strong, weak, or non-electrolytes. Our first question we're going to ask ourselves here is, do we see any ionic compounds? Well, I see potassium nitrate, and I see sodium acetate. So those are strong electrolytes. Do I see any strong acids? Well, there's hydrobromic acid, so that is a strong electrolyte. Do I see any strong bases? I see barium hydroxide, which I could have identified earlier as an ionic compound. It is definitely a strong electrolyte. Do I see any weak acids? I see nitrous acid, and I see acetic acid, so those are weak electrolytes. Are there any weak bases? Well, there's ammonia, and there's ethylamine, so those are weak electrolytes. And now the remaining 4 compounds are not acids or bases. They are covalent compounds, so therefore they are non-electrolytes. We have dimethyl ether, glucose, glycerol, and ethanol. These do not conduct electricity because they don't break up into ions at all. When solutions of an acid and a base are mixed together, a neutralization reaction occurs. In general, the reaction between an acid and a metal hydroxide produces water and a salt. In this section, we have a variety of neutralization reactions, and we're going to write the molecular, complete ionic, and net ionic equations. And we have to decide whether or not a substance should be broken up into ions. So substances that are strong acids or soluble ionic compounds should be broken up into ions, but if something is insoluble, is a pure solid or a pure liquid, or a weak electrolyte, then we do not break it up into ions. Let's start with a strong acid and a strong base. Hydrochloric acid is written as HCl. Sodium hydroxide is written as NaOH, and the products are water and sodium chloride. In the complete ionic equation, we break up HCl because it is a strong acid. We break up sodium hydroxide because it is a soluble ionic compound, a strong base. We don't break up water because it is a pure liquid. And we break up sodium chloride because it is a soluble ionic compound. We cross off the spectator ions, and then we have our net ionic equation. In our next example of a strong acid and a strong base, we have nitric acid, HNO3, reacting with calcium hydroxide, Ca, parentheses OH2. We produce water and calcium nitrate. We break up nitric acid because it is a strong acid. We break up calcium hydroxide because it's a soluble ionic compound. We don't break up water. And we break up calcium nitrate because it is soluble. Notice that I put coefficients into not only the molecular equation but also the complete ionic equation. Now when I cross off the spectator ions, I'm going to divide that entire reaction by 2, and we get the same net ionic equation that we had before. You would get this particular equation with any strong acid and strong base. Now moving on to a weak acid and a strong base, we have acetic acid, CH3COOH. We have potassium hydroxide, KOH, producing water and potassium acetate. Now I could write potassium acetate as KC2H3O2, but I'm choosing to write it this way, which looks a little bit strange because I'm focusing on the formula for acetic acid and just adding that potassium on the end, even though in many ionic compounds the metal or the cation comes first. Alright, now do we break up acetic acid? No, it is a weak electrolyte. We do break up potassium hydroxide, we don't break up water, it's a pure liquid, and we do break up the soluble potassium acetate compound. So after we cross off the spectator ions, this is our net ionic equation. The weak acid is written as the entire formula, then we have just hydroxide to produce water and a negative anion that came from the weak acid. Alright, our next example of a weak acid and a strong base, nitrous acid, so HNO2, barium hydroxide, Ba parentheses OH2. It produces water and barium nitrite. We do not break up nitrous acid because it is a weak electrolyte. We do break up the soluble barium hydroxide, and we also break up the soluble barium nitrite. Again, notice that I've put in the coefficients to balance the equation. After crossing off the spectator ion, this becomes our net ionic equation. I just divided everything by 2. So we have the complete formula of a weak acid plus just the hydroxide ion to produce water and the negative anion that came from the weak acid. Alright, let's take a look at strong acid and weak base. So we have hydrobromic acid, HBr, reacting with ammonia, NH3. But this time we're not going to produce water because there is no hydroxide ion. The ammonia becomes ammonium, and the other ion would be, in this case, bromide. So we form ammonium bromide. We do split up hydrobromic acid, but we do not split up ammonia. Ammonium bromide is a soluble ionic compound, so it is broken up into ions. Crossing off the spectator ions gives us the net ionic equation. So H plus from a strong acid plus ammonia to produce the ammonium ion. In our next example, we have a weak base, which is methylamine, reacting with a strong acid, chloric acid HClO3, methylamine CH3NH2, and it produces the methylammonium ion as well as the chlorate ion. But when this is written as one formula, which looks kind of strange, This is the methylammonium chlorate combination, written as one formula. We're going to split up chloric acid because it's a strong acid. We leave methylamine exactly as it is, and we split up the methylammonium ion and the chlorate ion. Crossing off the spectator ion, we get the net-ionic equation. H plus the methylamine to produce the methylammonium cation. Alright, our last example of these types of reactions is weak acid, so hydrofluoric acid, HF, plus a weak base, ammonia, NH3. We're going to produce ammonium fluoride, but we don't break up either the acid or the base. We do break up the soluble ionic compound, ammonium fluoride. But now you can notice there is nothing to cross off on either side. There are no spectator ions. So we get the same net-ionic equation. Certain anions can react with acids to produce a gas. And here are three examples of gases that can be formed with acid-base reactions. The first gas is hydrogen sulfide gas. The second one is carbon dioxide gas. And since CO3 2- or carbonate looks very similar to the sulfite ion SO3 2-, it should be no surprise that we produce a similar gas in terms of its formula. So not CO2, but rather SO2, sulfur dioxide. One more example of a gas that you could form, which I didn't mention in this packet, we saw that gas in the lab, and that would be the formation of ammonia. If ammonium reacts with a strong base, you would get release of ammonia gas. Now, as far as this particular gas-forming reaction, we know we're going to produce carbon dioxide gas. Sodium carbonate, Na2CO3, reacts with a strong acid, HCl, to produce sodium chloride and water and carbon dioxide. I'll put in the coefficients. I'll decide what needs to be split up and what stays together. Sodium carbonate is a soluble ionic compound, so it is broken up into ions. We break up HCl because it's a strong acid. We break up sodium chloride because it's a soluble ionic compound. And we don't break up a pure substance like water or CO2 gas. Crossing off the spectator ions, this is the net-ionic equation for the formation of carbon dioxide. A carbonate ion reacts with H plus ions in the form of a strong acid to produce water and CO2. Now we're on to section 4.4, and this is on redox reactions or oxidation reduction reactions. In terms of the definition of oxidation and reduction, this is on page 131. Loss of electrons is called oxidation. Gain of electrons is called reduction. Here is a mnemonic device for you. So we have a picture of an oil rig, and you can remember that oxidation is the loss of electrons and reduction is the gain of electrons. So when an element loses electrons, it becomes oxidized. When it gains electrons, it becomes reduced. When calcium reacts with oxygen to form calcium oxide, calcium starts out as 0 in its oxidation state. But calcium oxide, it carries a +2 oxidation state. So calcium is being oxidized from 0 to +2, and oxygen is being reduced from 0 to -2. When sodium reacts with chlorine, sodium is oxidized from 0 to +1, and chlorine is reduced from 0 to -1. Let's take a look at this general rule. When the oxidation number increases, we call that oxidation. When the oxidation number decreases, that is called reduction. Now we have a table in which we have to fill in oxidation numbers for each element. Let me call your attention to page 132, and there are some rules for assigning oxidation numbers for various elements and various compounds. If you have an atom and it's not bonded to anything else as an element, the oxidation number is always 0. If you have a monoatomic ion, then the charge on the ion is in fact the oxidation number. So S2- has an oxidation number of -2 and so forth. So we have 0 for iron, zinc, and oxygen, and we have +3, -2, and +2 for these monoatomic ions. The next thing we see in terms of rules is what to do when you have a nonmetal. Generally speaking, nonmetals have negative oxidation numbers, although they can certainly be positive. We're going to let oxygen be -2 for most ionic and molecular compounds. The major exception is a peroxide in which oxygen is -1. We're going to let hydrogen usually be +1 except when it's bonded to metals. If it's bonded to a metal, then hydrogen carries a -1 charge or oxidation number. And then fluorine is always -1 because it's the most electronegative atom on the whole periodic table, so that's going to be locked in at -1. The other halogens, chlorine, bromine, iodine, they would be -1 in most binary compounds, but if they are combined with oxygen or with fluorine, then the halogens are going to have positive oxidation states. All right, here we have water. H is +1 and O is -2. No problems there. But our next example is hydrogen peroxide. So what's going to change is that oxygen is now -1. Now we have oxygen bonded to fluorine, but we said that fluorine is always -1, so that means in this compound, oxygen carries a +2 oxidation state. And finally, we have hydrogen, which is bonded to a metal. In this case, the metal will be positive, so sodium is +1, and hydrogen is -1. In methane, CH4, we're going to go ahead and let hydrogen be +1, and carbon now has to be -4. But in carbon dioxide, if we let oxygen be -2, then carbon is +4. So in these two examples, you can see that carbon can exist in its most reduced state as methane and in its most oxidized state as carbon dioxide. All right, well now we come to polyatomic ions, and we're not trying to get the total of the oxidation numbers to equal 0, but rather whatever the overall charge on the ion is, in this case -1. So the sum of the oxidation numbers in all neutral compounds is 0, but the sum of the oxidation numbers in a polyatomic ion equals the charge on the ion. So we have -2 for oxygen and +1 for hydrogen. That works out. But for chlorate, let me just kind of show you how this works. You have 3 times -2, which gives you -6, and the oxidation state of chlorine is going to have to be a positive number, but not +6, rather +5, because that will give you the overall charge you're looking for. Similarly, if I have 1 nitrogen and 3 oxygens in nitrate, and the overall charge is -1, that means that nitrogen will be +5, and oxygen is -2. All right, we have carbonate, so -2 for oxygen and +4 for carbon. Chromate carries a +6 on the chromium. And here we have something called the oxalate ion. Let's work this out. There is carbon, which we don't know. There is oxygen, which is -2, and we have 4 of them. That's -8. But the total charge on the ion is -2. That means that those 2 carbons together equal +6. But when you're writing an oxidation number, it is what each atom is worth, which in this case is +3. All right, in phosphate, it's going to be +5 for phosphorus. In the bicarbonate ion, we get +1 for hydrogen. We get -2 for oxygen, and that forces carbon to be +4. Ammonium, the nitrogen is -3. In hydrazine, or N2H4, the hydrogen is +1, and the nitrogen is actually -2. And then we have hydroxylamine. Hydrogen's +1, oxygen's -2, and that forces the nitrogen to be -1. So you can see a variety of oxidation states for nitrogen, everywhere from -3 all the way up to +5. It has a range of values depending on what it's bonded to. This is nitrite. and the oxidation number on nitrogen is +3, and this is nitrate, and the oxidation number is +5. So let's note that when you increase the number of oxygen atoms bonded to another element, the oxidation number on that element increases. And then we'll go ahead and fill in the remaining oxidation numbers here. Chlorine is +7 in perchloric acid. Carbon is -2 in ethanol. Sulfur is either +4 or +6. When you change from sulfurous acid to sulfuric acid, you're again increasing the number of oxygen atoms and increasing the oxidation number on the element that's bonded to it. All right, well now we come to redox reactions. So we're looking for both oxidation and reduction. In this case, magnesium is oxidized from 0 to +2, and hydrogen is reduced from +1 to 0. In this next example, we have lead, sulfur, hydrogen, and oxygen. Now you might start by thinking, what's not changing in this particular reaction? Well, the lead is +2 on both sides. And the hydrogen is +1 on both sides. So what is changing is sulfur is changing from -2 to +6, so it's being oxidized, and oxygen is being reduced from -1 in peroxide to -2 in water. Is this reaction redox? Well, let's take a look. We have iron, sulfur, hydrogen, nitrogen, and oxygen. Let's take a look at the oxidation numbers for each element. For iron, it's +2 on both sides. For sulfur, it is -2 on both sides of the equation. Hydrogen is +1, nitrogen is +5 in nitrate, and oxygen is -2. So this is not a redox reaction because there are no changes in the oxidation numbers. For each of the following, we have to determine if it's redox, therefore, what's changing, and there has to be both. If you see an element being oxidized, then there must be an element that's being reduced. They occur in pairs. Nitrogen is -3 on both sides. Hydrogen is +1, chlorine is -1, sodium is +1, and oxygen is -2. So once you feel confident in assigning oxidation numbers to all of these compounds, you can then conclude that no, this is not a redox equation. Here it's a little more obvious that copper is going from 0 to +2. Silver is going from +1 to 0. The nitrogen is part of nitrate, so that's not changing the nitrogen or the oxygen. But this is a redox equation. Copper is being oxidized, silver is being reduced. In our next example, we have chlorine changing from 0 to -1. We have bromine changing from -1 to 0. And the potassium is not changing. This is a redox in which bromine is being oxidized and chlorine is being reduced. Remember, when the oxidation number increases in value, that's oxidation. When the oxidation number decreases in value, that's reduction. Then finally, we have a whole bunch of elements here: calcium, carbon, oxygen, hydrogen, sulfur. Calcium's not changing. Carbon is +4 on both sides. Oxygen is not changing, and neither is hydrogen or sulfur. So that would not be a redox equation because there are no changes. Now we're going to write the net-ionic equation for a reaction. We have to decide if we split something up or not. Well, aluminum is just aluminum, but hydrobromic acid is a strong acid, so we're going to go ahead and split it up. And aluminum bromide is a soluble ionic compound, so we split that up. We leave hydrogen as hydrogen gas. Let's cross off any spectator ions we see, and the net ionic equation looks like this. Here's iron. Just go ahead and write iron. We're going to go ahead and split up nickel nitrate as a soluble ionic compound, as well as iron, Roman numeral 2, nitrate. So those are going to be split up into ions, and we just have nickel by itself. Crossing off the nitrate as a spectator ion, this becomes the net net-ionic equation for that reaction. So this is table 4.5 in your book, and it lists an activity series of metals in aqueous solution. At the top of the list are elements like lithium and potassium, and at the bottom are platinum and gold. So which of these more likely are going to react by losing electrons? Well, the elements at the top are more easily oxidized. So if an element is higher than another in terms of this list, then the metal that's higher is going to give up its electrons, and the metal that's lower down would accept electrons. All right, let's take a look at letter K. Says, use the activity series to determine if a reaction occurs. Now, tin metal starts out as oxidation state 0. Magnesium nitrate, magnesium starts out as positive 2. If this reaction occurs, tin would have to be oxidized and magnesium would have to be reduced. Let's go find tin and magnesium on the activity series. That reaction may or may not occur. Let's take a look. So there is tin and there is magnesium. So what does this tell us? That magnesium is oxidized more easily than tin. Therefore, this reaction does not occur because magnesium, again, is oxidized more easily than tin. So no reaction occurs. All right, the next example that we see, aluminum would have to start out as 0, oxidation state, and copper chloride, copper is positive 2. If the reaction occurs, aluminum would become oxidized and copper would be reduced. Let's go find aluminum and copper on the activity series. Well, there's aluminum and there's copper. So since aluminum is oxidized more easily than copper, then this reaction does occur. All we have left to do is balance the equation by sticking in the appropriate 2's and 3's on both sides. Okay, our next example is zinc reacting with hydrobromic acid. Now you might think, how do I know whether it's going to be the hydrogen or the bromine that's involved? Well, hydrobromic acid has an H+1 and a Br -1. Zinc is clearly starting out as 0. Zinc would have to be oxidized to +2. Bromine cannot be reduced from -1 to -2 or -3. So if anything is going to be reduced in hydrobromic acid, it's going to be the hydrogen. So the reaction, if it does occur, would look like this. Zinc being oxidized and hydrogen being reduced. Let's go find zinc and hydrogen on the activity series. So there is zinc and there is hydrogen. Yes, zinc is oxidized more easily than hydrogen, so this reaction would occur, and we'll just go ahead and put a 2 in front of the hydrogen on the left. And our last example is another acid. This is hydrochloric acid, and we're trying to react platinum metal. Let's see if platinum is going to be oxidized in the presence of an acid. Well, as you can see, platinum is way down at the bottom, so platinum is not going to be oxidized. Instead, hydrogen is more oxidized, is easily oxidized compared to platinum, so this reaction would not occur. Hydrogen is oxidized more easily than platinum. Okay, we have now come to the end of section 4.4. I hope you found these answers and explanations helpful to you. Good luck with your studying and review of Chapter 4. Thanks for watching.